Linear Algebra II, Tutorial 9, Second-order curves and surfaces. Problem 1. Determine which second-order curve in E2 is given by the equation x1 squared plus 4x1 x2 plus x2 squared is equal to 1. Also, determine the minimal distance from a point on this curve to the origin, and also all points on the curve for which this minimal distance is attained. Solution. We start by writing the matrix for the quadratic form Q, which defines our curve. And we write this matrix in the standard basis of E2. So the matrix has 1, the coefficient here at position 1, 1, 1 at position 2, 2, and 4 divided by 2, which is 2, in positions 1, 2, and 2, 1. So the matrix is 1, 2, 2, 1. And in order to solve the problem, we need to diagonalize this matrix in some orthonormal basis. So let's start by computing the characteristic polynomial of this matrix. So this is a determinant of the matrix 1 minus x, 2, 2, 1 minus x. So this determinant is equal to 1 minus x squared minus 2 squared. So this is a difference of two squares. So this is equal to 1 minus x minus 2 times 1 minus x plus 2. Or in other words, the characteristic polynomial of our matrix is equal to 3 minus x times minus 1 minus x. So we have two eigenvalues, lambda 1 is equal to 3 and lambda 2 is equal to minus 1. Both these eigenvalues have algebraic multiplicity 1. So the diagonal form of our matrix is the diagonal matrix with 3 and minus 1 on the main diagonal. So the signature of our quadratic form is 1, 1. So we have one positive eigenvalue and one negative eigenvalue, which means that our curve is a hyperbola. And in our new coordinates, after this orthonormal change of basis, the equation for our curve is 3 times y1 squared minus y2 squared is equal to 1. So the maximal eigenvalue is lambda 1, which is equal to 3. Therefore, the minimal distance from a point on the curve to the origin is 1 divided by the square root of 3. So it's always 1 divided by the square root of the maximal eigenvalue. In order to find at which points this minimal distance is attained, we need to determine the eigenvectors for our matrix with this eigenvalue 3. So we subtract 3 on the main diagonal and get the matrix minus 2, 2, 2, minus 2. And the eigenvectors are exactly the solutions to the homogeneous system of linear equations determined by this matrix. It is easy to guess one solution, which is 1, 1. So minus 2 plus 2 is 0, and 2 minus 2 is 0. And since the algebraic multiplicity is 1, this is a unique up to scalar linearly independent solution. We norm it, so we take the vector v and divide by its length. So the length here is a square root of 1 squared plus 1 squared, which is 2. So the normed eigenvector is 1 divided by the root of 2 times 1, 1. And so the points on our hyperbola that are closest to the origin are exactly the points. We take this normed eigenvector and multiply with plus minus the distance to the origin. So these are the points plus minus 1 divided by the square root of 3 times 1 divided by the square root of 2 times our vector 1, 1. So we get the points plus minus 1 divided by the square root of 6 times the vector 1, 1. And this completes the solution to problem 1. Problem 2. Determine which second-order surface in E3 is given by the equation x1 squared plus 2x1 x2 plus 2x2 x3 plus x3 squared is equal to 1. Also, determine the minimal distance from a point on the surface to the origin, and also all points on the surface for which this minimal distance is attained. Solution. We always start such a problem by writing down the matrix in the standard basis of our Euclidean space for the quadratic form which defines our surface or curve. So in our case, we have a surface, so we have a 3 times 3 matrix. So the diagonal elements are 1 here, then there is nothing at x2 squared, so 0, the second diagonal element, and the coefficient at x3 squared is 1. So the diagonal elements are 1, 0, and 1. Then we take 2, the coefficient at x1, x2, divided by 2, we have 1 and 1, and write 1 in position 1, 2, and 1 in position 2, 1. The coefficient at x1, x3 is 0, so we write 0 in position 1, 3, and 0 in position 3, 1. And finally, the coefficient at x2, x3 is 2, so we write 1 in position 2, 3, and 1 in position 3, 2. And we have the matrix 1, 1, 0, 1, 0, 1, 0, 1, 1. And we need to diagonalize this matrix in some orthonormal basis. So we compute the characteristic polynomial for this matrix. This is a determinant for the matrix 1 minus x, 1, 0, 1 minus x, 1, 0, 1, 1 minus x. So this determinant is equal to the product 1 minus x times 1 minus x. Then the next two positive summands are 0 and 0. Then the negative summand 0. And then minus twice the summand 1 minus x. So this is our determinant. We can move 1 minus x out to get 1 minus x times x squared minus x minus 2. And so the characteristic polynomial for our matrix is equal to 2 minus x times 1 minus x times minus 1 minus x. So we have three eigenvalues. Lambda 1 is equal to 2, lambda 2 is equal to 1, and lambda 3 is equal to minus 1, all with algebraic multiplicity 1. So the diagonal form for our matrix is a diagonal matrix with 2, 1, and minus 1 on the main diagonal. So the signature of this matrix is 2, 1. We have two positive eigenvalues and one negative eigenvalue. Therefore, the surface, which is defined by this quadratic form, is a hyperboloid of one sheet. And the equation in the new coordinates is 2y1 squared plus y2 squared minus y3 squared is equal to 1. So the maximal eigenvalue is lambda 1, which is equal to 2, and therefore the minimal distance from our surface to the origin is 1 divided by the square root of 2. To determine the points at which this distance is attained, we need to find all eigenvectors for this eigenvalue. So the eigenvectors for this eigenvalue are the solutions to the homogeneous system of linear equations given by the matrix when we take the matrix of the form and subtract 2 on the main diagonal. We get the matrix minus 1, 1, 0, 1 minus 2, 1, 0, 1, minus 1. And here again, it's easy to guess that the vector 1, 1, 1 is a solution to the system, because minus 1 plus 1 is 0, 1 minus 2 plus 1 is 0, and 0 plus 1 minus 1 is 0. We norm this vector, so we divide it by its length, which is the square root of 3, and get the vector 1 divided by the square root of 3, 1, 1, 1. So this is unique up to plus minus, normed eigenvector with eigenvalue 2. And so to get the points on our surface which are closest to the origin, we take this normed eigenvector and multiply with plus minus the distance, the minimal distance from the surface to the origin. So we get plus minus 1 divided by the square root of 2 times 1 divided by the square root of 3 times 1, 1, 1. So the points are plus minus 1 divided by the square root of 6, 1, 1, 1. This completes problem 2. Problem 3. Determine which second-order surface in E3 is given by the equation x1 squared plus x2 squared plus x3 squared plus 4x1 x2 plus 4x2 x3 plus 4x1 x3 is equal to 1. Show that this is a rotational surface and determine the rotation axis. Also, determine the minimal distance from a point on the surface to the origin, and also all points on the surface for which this minimal distance is attained. Solution: we start by writing down the matrix of the quadratic form which defines this surface. So we have 1, 1, 1 on the main diagonal, and all other coefficients are 4, so if we divide we will get 2. So outside the main diagonal, all other elements of the matrix are 2. So the matrix is 1, 2, 2, 2, 1, 2, 2, 2, 1. And we need to diagonalize this matrix in some orthonormal basis. So we compute the characteristic polynomial for this matrix. It's the determinant of the matrix 1 minus x, 2, 2, 2, 1 minus x, 2, 2, 2, 1 minus x. So this determinant is equal to 1 minus x cubed plus 8, so plus 16, minus 4 times 1 minus x, and this we should subtract 3 times, so minus 12 times 1 minus x. When we compute this polynomial, we will get minus x cubed plus 3x squared plus 9x plus 5. And here we can readily see that minus 1 is a root, and then 5 is a root, and minus 1 is a root of order 2. So the polynomial is equal to 5 minus x times minus 1 minus x squared. So we have two eigenvalues, lambda 1 equal to 5 with algebraic multiplicity 1, and lambda 2 equal to minus 1 with algebraic multiplicity 2. Since we have an eigenvalue of multiplicity 2, this is a rotational surface. And to determine the rotation axis, we need to find the eigenvector for the other eigenvalue, for the eigenvalue with multiplicity 1. So this is the eigenvalue lambda 1 is equal to 5. So the eigenvectors for this eigenvalue are the solutions to the homogeneous system of linear equations, whose matrix is obtained from the matrix of our form by subtracting 5 on the main diagonal. So we get the matrix minus 4, 2, 2, 2 minus 4, 2, 2, 2, minus 4. And here it is easy to see that 1, 1, 1 is a solution, because minus 4 plus 2 plus 2 is 0. 2 plus minus 4 plus 2 is 0. 2 plus 2 minus 4 is 0. So we have a solution 1, 1, 1. This is the one of the eigenvectors for the eigenvalue 5. And therefore the rotation axis is a line which is spanned by this vector. So the rotation axis for our surface is a line a times 1, 1, 1, where a is a real number. So the diagonal form, we know that we have one eigenvalue 5 with multiplicity 1, and the second eigenvalue minus 1 with multiplicity 2. The diagonal form for the matrix of our quadratic form is the matrix with 5, minus 1, and minus 1 on the main diagonal. So the signature is 1, 2, 1 positive, 2 negative eigenvalues. Therefore, our surface is a hyperboloid of 2 sheets. And the equation for our surface in the new coordinates is 5y1 squared minus y2 squared minus y3 squared is equal to 1. The maximal eigenvalue is lambda 1 is equal to 5, and therefore the minimal distance from the surface to the origin is 1 divided by the square root of 5. We already know that 1, 1, 1 is an eigenvector, and in order to determine the points on the surface which are closest to the origin, we first normed this eigenvector, so we divide it by its length, and the length is the square root of 3. So the normed eigenvector is 1 divided by the square root of 3, 1, 1, 1. And then the points on our hyperboloid that are closest to the origin are plus minus the distance, 1 divided by the square root of 5, times the normed eigenvector, which is 1 divided by the square root of 3, 1, 1, 1. So we get the points plus minus 1 divided by the square root of 15, 1, 1, 1. This completes problem 3. Problem 4. Determine which second-order surface in E3 is given by the equation 2x1 squared plus 3x2 squared plus 2x3 squared plus 2x1 x3 is equal to 1. Show that this is a rotational surface and determine the rotation axis. Also, determine the minimal distance from a point on the surface to the origin, and also all points on the surface for which this minimal distance is attained. Solution. We have the following matrix in the standard basis of our Euclidean vector space E3 for the quadratic form Q, which defines our surface. So we have coefficients 2, 3, and 2 on the main diagonal. Then we have here 2 at x1, x3, so we write 1 in position 1, 3, 1 in position 3, 1, and the rest is 0. So we get the matrix 2, 0, 1, 0, 3, 0, 1, 0, 2. And we need to diagonalize this matrix in some orthonormal basis. So we compute the characteristic polynomial. This is a determinant for the matrix 2 minus x, 0, 1, 0, 3 minus x, 0, 1, 0, 2 minus x. So this determinant is equal to the product here on the main diagonal, 2 minus x squared minus 3 minus x, minus the product on the other diagonal, 3 minus x. So if we move 3 minus x out, we get 3 minus x times 2 minus x squared minus 1. So this is 2 minus x minus 1 times 2 minus x plus 1. So we get 3 minus x squared times 1 minus x. We have two eigenvalues. Lambda 1 is equal to 3 with algebraic multiplicity 2, and lambda 2 equal to 1 with algebraic multiplicity 1. Since we have an eigenvalue of multiplicity 2, this is a rotational surface. The rotation axis, we need to find the eigenvector for the other eigenvalue, for the eigenvalue with multiplicity 1. This is lambda 2 is equal to 1. The eigenvectors for this eigenvalue are the solutions to the homogeneous system of linear equations, whose matrix is obtained from our matrix by subtracting 1 on the main diagonal. So we get 1, 0, 1, 0, 2, 0, 1, 0, 1. So here again, it's very easy to guess that 1, 0, minus 1 is a solution, because 1 minus 1 is 0, 0 here, 1 minus 1 is 0. So we have a solution 1, 0, minus 1, and therefore the rotation axis is a line in our space spanned by this vector. So it's a line a times 1, 0, minus 1, where a is a real number. So the diagonal form for the matrix of our quadratic form is the diagonal matrix with 3, 3, and 1 on the main diagonal. The signature of the quadratic form is 3, 0. We have 3 positive eigenvalues, which means that our surface is an ellipsoid. And in the new coordinates, the equation for our surface is 3y1 squared plus 3y2 squared plus y3 squared is equal to 1. So the maximal eigenvalue is lambda 1, which is equal to 3. Therefore, the minimal distance from the surface to the origin is 1 divided by the square root of 3. However, this eigenvalue has algebraic multiplicity 2, which means that we have the whole circle of points which are closest to the origin. So we have to determine all these points on that circle. So they are obtained by rotation. This is a rotational surface, and the maximal eigenvalue has algebraic multiplicity 2. So let's determine all eigenvectors for this eigenvalue. We take the matrix of our curve, we subtract 3 on the main diagonal, and we get the matrix minus 1, 0, 1, 0, 0, 0, 1, 0, minus 1. And the eigenvectors are the solutions to the homogeneous system of linear equations with this matrix. It's easy to guess that we have two linearly independent solutions. R1 is 1, 0, 1, because minus 1 plus 1 is 0, it's 0 here, and 1 minus 1 is 0. And R2 is 0, 1, 0, because the second column is 0. So here are the two linearly independent solutions, and hence the general solution is just a linear combination of these two linearly independent solutions. the general eigenvector with eigenvalue 3 is a vector A, B, A, where A and B are real numbers. So we norm this vector. The length of the vector ABA is a square root of 2a squared plus b squared. So the normed version of the vector is 1 divided by the square root of 2a squared plus b squared times ABA. So this, for various a and b, these are exactly the length 1 eigenvectors with eigenvalue 3 for our matrix. So let's parameterize them for an angle t between 0 and 2 pi. We set a to be cos t divided by the square root of 2 and b to be sine of t. And then the square root of 2a squared plus b squared is 1, and we get the corresponding normed eigenvector to be cos t divided by the square root of 2, this is a, and then sine t, this is b, and then cos t divided by the square root of 2. So this is a parameterization of all normed eigenvectors for our matrix with eigenvalue 3. And so to get the points on our ellipsoid which are closest to the origin, we should multiply this vector with the minimal distance to the origin, which is 1 divided by the square root of 2. So the answer is that all these points are 1 divided by the square root of 2, cos t divided by the square root of 2, sine t cos t divided by the square root of 2, where t is an element between 0 and 2 pi. 0 is included and 2 pi is not included. And this completes problem 4. Here are some other problems and questions. Question 1. Determine which second-order curve in E2 is given by the equation 2x1 squared plus 2x1 x2 plus 2x2 squared is equal to 1. Also, determine the minimal distance from a point on this curve to the origin, and also all points on the curve for which this minimal distance is attained. Question 2. Determine which second-order surface in E3 is given by the equation x1 squared plus 2x2 squared plus x3 squared plus 2x1 x2 plus 2x2 x3 plus 4x1 x3 is equal to 1. Also, determine the minimal distance from a point on the surface to the origin, and also all points on the surface for which this minimal distance is attained. Question 3. Determine which second-order surface in E3 is given by the equation x1 squared plus x2 squared plus x3 squared plus 2x1 x2 plus 2x2 x3 plus 2x1 x3 is equal to 1. Show that this is a rotational surface and determine the rotation axis. Also, determine the minimal distance from a point on the surface to the origin, and also all points on the surface for which this minimal distance is attained. Thank you very much, and see you next time.